Welcome to our today's class. It is our second lesson on the topic magnetism. So as usual, let me commence by giving you the quote of the day, which states that, "Sorry, I don't have a solution for what you should do in order to live a happy life. Instead, I have a solution for what you should do in order to live a sad life which is full of regrets. And the solution is try pleasing everyone." So we'll discuss that quote at the end of our class today. So today we'll be looking at magnetic field patterns around various magnets. So let's remind ourselves of what we meant by the term magnetic field. So we did say that a magnetic field is just a region around a magnet where the force of attraction or repulsion are strongly felt. It is worth noting that a magnetic field is always indicated, or it is shown by the lines of force, or sometimes what we call the magnetic field lines. So let's start by the field pattern around a bar magnet. So this is our bar magnet. So the field, actually the lines of force for a bar magnet, they originate from the north pole and end at the south pole. So we looked at the properties of magnetic field lines, or the lines of force, and we did say that they will always originate from the north pole and end at the south pole. So the lines of force for a bar magnet will always originate from the north pole. This is our north pole, and end at the south pole. So you can see actually the direction of the lines of force. So the arrow is indicating the direction from which the lines of force are emanating from, and the direction to which actually the lines of force are ending to. So the lines of force are all originating from the north pole. So they originate from the north pole or emanate from the north pole. So you can see the arrow is pointing, the lines are pointing towards the south pole, so meaning that they are all originating from the north pole. So they are originating from the north pole and they end actually at the south pole. So if you look at the south pole, actually the lines of force are entering into the south pole. So the south pole acts as a recipient, whereas the north pole acts as a donor, that is for the lines of force. Also, when you are sketching lines of force, you must ensure that they should never cross each other. Remember we said that the other property of lines of force is that they do not cross each other. So what is the reason behind that? Remember, if all the lines of force are originating from the north pole, it means they are like poles. That is, they are all coming from the north pole. So if they are charged with a north pole, then it means if this is a north pole, then the other line is also acting like a north pole. It means they are like poles. And from the basic law of magnetism, we did say that like poles repel, and like poles attract each other. So because these are like poles, which are both originating from the north pole, it means they will always repel each other. So if you are drawing a magnetic field line, then you are allowing one line to intersect another line. You are simply saying that they are attracting each other, which is not true. So whenever you are drawing or you are sketching the lines of force, always ensure that one, they originate from the north pole. That is, the arrow should be pointing from the north pole and entering the south pole, because the lines of force originated from the north pole and end at the south pole. Also, the lines of force never intersect each other. Why? Because they repel each other sideways. So they repel each other sideways. And remember, the more the number of force, or the closer the number of force, the stronger the magnetic field. So we also did say that the magnetic field is stronger at the poles. So you can see the concentration, or the distance between any two lines of force actually at the north pole. They are very closer as compared to midway, actually the bar magnet. So the closer the lines of force, the stronger the magnetic field. Also, the more the number of lines of force, the stronger the magnetic field. So a magnet can be drawn. Maybe you can be drawn two magnets, one having 3 lines of force, then another one having 5 lines of force. Then you can be asked to state which magnet has a stronger magnetic field. So the magnet with many number of lines of force actually is the magnet with a stronger magnetic field. So for a bar magnet, the most important thing is to note that the lines of force will always originate from the north pole and end at the south pole. So if you are sketching lines of force also, don't just draw lines without arrows. We must see the arrows. So the arrows indicate the the direction in which the lines of force are moving from and towards. So the arrows must be indicated for you to earn full marks. Then B, we look at the field pattern between unlike poles. So what do we mean by unlike poles? So from our previous class, we did say that unlike, when we say that two things are unlike, it means they are not sharing any properties. They don't have common properties, or they are not similar. Yeah. So when we are talking of unlike poles, in this case, we did say that a magnet has two poles. That is the north pole or the north seeking pole, and the south pole, or sometimes what we call the south seeking pole. So if we are talking of unlike pole, we mean maybe a north pole placed closer to a south pole, or a south pole placed closer to a north pole. So those are unlike poles. Remember, if we are talking of like, we will mean maybe a north pole with a north pole, or a south pole with a south pole. So if you are talking of unlike poles, it means they are opposite poles. So that's why you are seeing here we have a bar magnet with a north pole placed closer to a south pole. So a north pole and a south pole, these are actually unlike poles. So how do the field pattern arrange themselves in unlike poles? So remember, from the basic law of magnetism, we did say that unlike poles will always attract each other. So you can see that the line of force will always originate from the north pole, and they are attracted towards the south pole. So the arrows are very important in this case. So if you are asked to sketch a magnetic field pattern around two unlike poles, this will be the appearance. So it is important to know that the lines of force always originate from the north pole, and they enter, or they end at the south pole. So for a magnetic field pattern between unlike poles, each magnet has its own magnetic field. So the first magnet here had its own magnetic field, then the second magnet here also had its own magnetic field. Then the two fields actually combine to produce a single magnetic field. So actually this magnetic field is maximum because it is a combination of the field of the first magnet with the field of the second magnet. So you cannot compare the strength of this magnetic field with the magnetic field of the first bar magnet here. Why? Because this is a combination. That is, the field of the first magnet has combined with the fields of the second magnet. So they combine each other, because unlike poles will always attract each other. So the most important thing is to know that the lines of force originate from the north pole and end at the south pole, as shown in this particular diagram. So this for the case using two bar magnets. So we can conduct such a similar experiment but using a horseshoe magnet. Where is the word horseshoe actually coming from? So we call it a horseshoe magnet because it is in the shape of the shoe of a horse. If you've looked at the foot of a horse, you will actually see that it is in this particular shape. It is somehow circular in this particular shape. So hence the name a horseshoe magnet. Why a horseshoe magnet? Because it is in the shape of the shoe or the foot of a horse. A horse, I think, is just an animal. Then for a horseshoe magnet, something happens. So similarly, actually the lines of force will originate from the north pole towards the south pole. But because for a horseshoe magnet, actually the poles are very closer to each other, it means the field in this case will be stronger as compared to the field above here. Why? Because the lines of force are closer to each other, because the polarities, that is the north pole, is very closer to a south pole. Unlike for a bar magnet, where a north pole is to the far end, the other south pole is to the far end. So the closer the polarities, the closer the poles, the stronger the magnetic field. So we are saying that for a horseshoe magnet, the direction of the lines of force is from the north pole to the south pole. Then the field lines between the poles being more concentrated. So the field lines are more concentrated because the lines of force, or the polarities, are very closer to each other. Therefore, a horseshoe magnet is therefore more powerful than a bar magnet. So you can be asked to give a reason why a horseshoe magnet is more powerful than a bar magnet, or why the magnetic field in a horseshoe magnet is stronger than the magnetic field in a bar magnet. So the reason is simply because that for a horseshoe magnet, the lines of force between the poles are more concentrated. So if they are more concentrated, it means the magnetic field would be stronger. So the reason is because in a horseshoe magnet, the poles are closer to each other. That is, the south pole is closer to the north pole. Therefore, the lines of force are very concentrated. So you can see here that the lines of force actually are very closer to each other and very concentrated. So there are many lines of force. So we also did say that the number of lines of force, the stronger the magnetic field. So you can see here that the lines of force are 1, 2, 3, 4, 5, 6, 7, as opposed to 1, 2, 3, 4, 5, 6. So clearly you can see that here the lines of force are many, indicating that the magnetic field is stronger. So we are saying that a horseshoe magnet is more powerful than a bar magnet, because for a horseshoe magnet, the lines of force, because the poles are closer to each other, therefore the lines of force are more concentrated. The lines of force are more concentrated. C, we look at the field pattern between like poles. Remember we said like, the word like means similar or identical or sharing some common properties. So if you are talking of like poles, we mean poles which are similar or poles which have same characteristic. So for example, we said we have two types of poles, a north pole and a south pole. So if you bring two north poles closer to each other, then those ones are called like poles. If you bring two south poles together, those are also like poles. Why? Because it is a north pole closer to a north pole and also a south pole closer to a south pole. So here we are bringing a north pole closer to another north pole. So we want to see the field pattern between two like poles, or even more, two or more like poles. So whenever the like poles are placed adjacent or closer to each other, as shown in this particular diagram here, the lines do not actually cross each other. Lines from one pole are deflected by the lines from the other pole. So you can see the lines of force from the north pole of the first magnet are repelled by the lines of force from the second magnet. So the lines actually repel each other. Why? Because they are both coming from the north pole. Therefore it means they have similar polarity. So if this is a north pole, then this is also having properties of a north pole. Then remember that north pole with a north pole, or like poles, will always repel each other according to the basic law of magnetism. So they repel each other away from each other, meaning a region will remain between those two magnets without a magnetic field, or whose magnetic field is actually zero. So when two poles are placed adjacent to each other, the lines do not cross each other. Therefore the lines from one pole are deflected by the lines from the other pole. So this indicates repulsion. So when they are placed together, they actually repel each other. So this is what we are calling, to repel is to move away from each other. So this one is moving sideways, then this one is also moving in this direction, this one is moving in that direction, then this line of force is moving in this direction. So they are actually repelling each other, because like poles will always repel each other. Now there is no field at the point marked X, that is the point between those two bar magnets. So because the lines of force are all repelled away, it means this region will remain with zero lines of force. And remember, the lines of force are the ones that indicate the presence of a magnetic field. So if this region is having no lines of force, it means the magnetic field at point X is actually zero. Therefore that point, that is a point where the resultant magnetic field is zero, we call it a neutral point. So point X is actually neutral. So there is no field at a point marked X, which is called the neutral point. So at the neutral point, the resultant or the summation of the lines of force, or the resultant magnetic field, is actually zero. Reason being, all the lines of force are repelled away. Then D, we look at effects of soft iron rod and ring. So first of all, we start with this is a soft iron rod. This is our soft iron rod. So if a north pole is brought close to, before I move to that, a similar experiment can be carried out. That is in C, between like poles. They can use a south pole with a south pole. So if they are using a south pole with a south pole, the pattern will still exactly be the same, but the only thing that will change is the direction of the lines of force. So if it was a south pole closer to a south pole, then these arrows will be pointing towards the south pole, because remember that lines of force originate from the north pole and end at the south pole. So if you are brought a question with a south pole closer to a south pole, just draw the same pattern, but change the reverse the direction of the pointing of these arrows. So the lines of force will be pointing towards the south pole, and also this one towards the south pole, but the neutral point will still be there. Why? Because south with the south, those are still like poles which will always repel each other. So the effect of soft iron rod. So this is our soft iron rod. So if a soft iron rod is brought closer to any pole of a magnet, this will be the expected observation. So if it is brought close to a north pole, actually the lines of force start from the north pole and go through the soft iron rod and emerge from the other end. So the reason being, to some extent, the soft iron rod being a magnetic material, it is actually induced with some of the magnetic forces. So we are saying that the lines of force from the magnet gets concentrated along the soft iron rod. So the lines of force from the north pole here, they get concentrated towards the soft iron rod. Then the lines emerge on the far end of the rod, thus preventing them from reaching some certain region. So the lines enter through the soft iron rod and they emerge from the other side. So remember, since this is a north pole, it means lines of force originate from the north pole. Therefore, the direction of the lines of force will actually be towards from the north pole. That's why you are seeing that the arrows are pointing away from the north pole. So the lines of force, they are pointing away from the north pole. Then they enter through the soft iron rod and they emerge from the other side. So if a similar experiment was conducted, but now with a south pole here instead of a north pole, what will happen is that the diagram will be the same. The only thing that will change is the arrow, the pointing of the arrow. So if you are using a south pole, the arrows are supposed to point towards the south pole, because the lines of force always emanate from the north pole and end at the south pole. So the only thing that will change is the direction of the arrow, but the other things will be the same. So here also the arrow will be pointing towards the south pole. That is if we use a south pole here instead of a north pole. Then Roman 2, effect of soft iron ring. So the effect of magnetic field lines on a soft iron ring. So this is our soft iron ring with remember, if it is a ring, it means there is some gap or some hole in between it. So that hole or that gap is what we are calling a P here. So a soft iron ring also concentrates the magnetic lines of force. That is as shown in this particular diagram. So we have the lines of force originating from the north pole and of course ending at the south pole. So because a soft iron ring concentrates the magnetic lines of force, this prevents the lines from entering region P. Thus, region P is said to be shielded by the ring from magnetic field. That is, the soft iron ring distributes the lines of force in such a manner that they do not enter, or region P is shielded. They do not enter the gap in between them. So the lines of force originate from the north pole, then they are concentrated in this manner, then they end at the south pole. So region P, no lines of force will cross within region P. So region P, we say it has been shielded. To shield is just to prevent the lines of force from entering a certain particular region. So if it is a soft iron rod ring, the region between it, or the gap between the ring, will actually be shielded from the lines of force. Therefore, both the iron rod and ring can be used in magnetic shielding or screening. So you can be asked to give an application of a soft iron rod or even soft iron ring. So the application is that a soft iron rod and a soft iron ring are used, or they are applied in magnetic shielding, or sometimes what we call screening. So some electrical measuring instruments and watches are shielded this way from stray magnetic fields using alloys of high magnetic permeability. The permeability is just the ability of the lines of force to go through a certain material. So the property of certain material to concentrate a magnetic field, hence leaving some areas totally free from the magnetic influence. That is what we call magnetic permeability. Then an alloy is just a combination of two or more metals, of course, which could be sharing some common properties. So that is how a soft iron ring, the lines of force will actually be prevented, or a certain region P will be shielded. It will be shielded. If a similar experiment was carried out, but now this side having a south pole, then the other side having a north pole, The diagram will still exactly be the same, but the only thing that will change will be the direction of the arrows, because the lines of force should originate from the North Pole towards the South Pole, but a region P will actually be shielded. A region shielded. The next we look at what we call the Earth's magnetic field. So the Earth also has its own natural magnetic fields. So if this is the North Pole, that is using a compass direction, if that is the true North Pole, then the magnetic field of the Earth will always point towards the North Pole. So the North Pole of a suspended magnet points roughly to the geographical north of the Earth. Then by the law of attraction, the Earth's content make up a magnet whose South Pole lies at the north. Therefore, a compass needle thus aligns itself in the direction of the Earth's magnetic field. So the Earth's magnetic field, that is its field, always point towards the North Pole. They point towards the North Pole. Also, remember that if you look at this Earth magnetic field, they are uniform. Remember we looked at types of field. We did say we have varying fields and uniform fields. So uniform fields are the one in which the magnetic force or the magnetic field is actually uniform. That is, the magnetic field at this lower point is the same as the magnetic field at the midpoint, and also the same as the magnetic field at the upper point. That is, the field is uniform throughout the whole magnetic field pattern. Therefore, Earth, the Earth field is a good example of a uniform field. So if you are asked to give an example of a uniform field, you simply say the Earth magnetic field, the Earth magnetic field. So if a bar magnet, so we are looking at bar magnet in Earth magnetic field. So if a bar magnet is placed anywhere near the Earth's surface, will have its magnetic field combined with the fields of the Earth. That is as shown here. So if I take a bar magnet closer to or within the magnetic field of the Earth, this is how they will actually combine each other. So at points marked X, the magnetic field of the Earth and that due to the magnet are equal and opposite. So at point X, this is our point X, this is also our point X, and this is also our point X in this particular diagram. So here you can see that the fields of the Earth, these are the Earth magnetic field, they're actually pointing upwards, whereas the fields of the magnet, of this magnet, are pointing downwards. Because it has a North Pole here, therefore it means the fields actually originate from the North Pole, then they move downwards towards the South Pole. So if you compare this field of the magnet and the field of the Earth, they are pointing, the field of the Earth are pointing towards the north or upwards, while the field of the magnet are pointing downwards. That's why we are saying they are equal and opposite. Therefore, they cancel each other. So if they cancel each other, it means this particular point X is actually neutral, or its magnetic field is actually 0. So the resultant magnetic field at point X is therefore 0. So point X, we call them neutral points. So these are neutral points. Also, this one is a neutral point. So neutral point simply means the fields are cancelling each other, therefore there is 0 magnetic field. However, at point P, remember point P is the point closer to our magnet here. So at point P, the fields of the magnet is stronger than that of the Earth, while is weak at point Q. So the field of the magnet at point P is stronger than the field of the Earth. Why? Because point P is very closer to our bar magnet. But at point Q, the field of the magnet is actually weaker. Why? Because point Q is further away from our magnet. It is further away from our magnet. Then next, look at lastly we look at what we call the domain theory. What we call the domain theory. So when a bar magnet is broken into 2 or more pieces, the pieces retain their magnetism, each having a North Pole and a South Pole at its end. So if I break this bigger magnet of mine here into 2 pieces, this will be the appearance. So each piece of the magnet actually retains its magnetism. That is, this other end was a South Pole. It means also the other end of the broken magnet will be a South Pole. Because this end was a North Pole, this end will be a North Pole. So if this is a North Pole, automatically the other end becomes a South Pole. But if this was a South Pole, automatically the other end becomes a North Pole. So if a bar magnet is broken into smaller pieces, each piece actually retains its magnetism as shown here. So south pole retains its pole, then north pole retains its pole, but the middle one gets opposite poles because a magnet has two polarities. That's a north pole with a south pole. So if I break further these other two pieces into tinier magnets, so the smaller magnets also retain their magnetism. So because this was a south pole, it means this one will also be a south pole. That is, the polarities are retained. This was a north pole, this will also be a north pole. So automatically the other side becomes a south pole and this side becomes a north pole. So if I also break this other magnet, this will be the pieces obtained which will retain their magnetism. That's a south pole, remains to be south, then north pole with north, then automatically this becomes a south pole, then this one becomes a north pole. So according to the domains theory, that when a bar magnet is broken into two or more pieces, the pieces retain their magnetism, each having a north pole and a south pole at its end. Then magnets consist of smaller, so let's look at the arrangement of the domains and even the dipoles within a magnet. So magnets consist of smaller magnetic groups referred to as magnetic domains. So these are what we are calling a domain. A domain is just a space within which the dipoles actually lie. So this is my first domain, this is my second domain, that is this region or this space. Then this is my third domain, and lastly this is my fourth domain. So this bar magnet here has actually four domains. That is 1, 2, 3, 4. So what is a domain? We are saying that magnets consist of smaller magnetic groups referred to as magnetic domains. So a magnetic domain is just a group. They are just smaller magnetic groups. So smaller magnetic groups, those are what we call magnetic domains, or just the spaces within a magnet whereby the dipoles align themselves. So the domains have a common magnetic axis, with one end being a north pole and the other end being a south pole. Then the domains vary in shape and sizes. Yeah. So the domains have one end being a north pole. For example, for this particular domain, its north pole is in this side. Why? Because the lines of force will always move from the north pole towards the south pole. So this is the south pole of this first domain, and this is the north pole of the first domain, and the south pole is somewhere here, because that is where the dipoles are entering into. So remember, the dipoles in this case represent the lines of force. Then for this particular domain here, its south pole, its north pole is here, because this is where the lines of force or the domains are originating from, or the dipoles, and the south pole is here because that is where the lines of force are entering. For this particular domain, the north pole is upwards, then the south pole is downwards. For this particular domain, the north pole is downwards, but the south pole is upwards. Now the subdivision of a magnet leaves each piece with some domains having a common axis. Yeah. Then the domains comprise smaller subatomic magnets called dipoles. So we are saying that within the domains we have smaller subatomic magnets called dipoles. Subatomic means it is even smaller than the size of an atom. So which means the dipoles are actually minute or very small. They are subatomic. Remember, an atom is already smaller, but we are subdividing it, the divisions of an atom. So a dipole, these are just smaller subatomic magnets, the smaller subatomic magnets found within the domain. So the dipoles are actually located within the domains, as we are seeing here. So like our first domain here has 1, 2 dipoles. Our second domain here also has 2 dipoles. Our third domain here has 2 dipoles, and also our fourth domain here has actually 2 dipoles. So the dipoles in a particular domain point in a common direction. Yes, as you can see here. So in my first domain here, actually the 2 dipoles are pointing in a common direction. In the second domain here, the 2 dipoles are also pointing in a common direction. In my third domain here, the 2 dipoles are pointing in a common direction. In my fourth domain here, the 2 dipoles are also pointing in a common direction. So the dipoles in a particular domain always points towards a common direction. So in the unmagnetized state, that is when a material is not magnetized or when it has no magnetism. So in the unmagnetized condition or state, the dipoles arrange themselves in closed loops. Then the resultant magnetic magnetism of all the domains in each state is actually 0. So in this state, the net or the total magnetism in that particular magnet will be 0. Why? Because the domains are arranged in different directions. So this domain is facing this direction, these other domains are facing in this direction, the other domains are facing downwards, the other domains are facing upwards. So these two domains will cancel the magnetic effect of these other two domains. Why? Because they are equal, yes, but pointing in opposite direction. So they are equal and opposite, therefore their magnetic field is actually cancelled. Therefore the net magnetic field within these two domains will be 0. Also, these ones are pointing downwards, these other two are pointing upwards. So remember, these are equal number of dipoles, but they are pointing in opposite direction. Therefore it means they will cancel each other, so their magnetic effect cancels out. Therefore the net or the resultant or the total magnetism or magnetic field within a magnet in unmagnetized state will be 0. It will be 0. Why? Because the dipoles are aligned in opposite direction or in different direction. Therefore we say this is unmagnetized state. Unmagnetized is the opposite of being magnetized. So later on we look at methods of magnetization. Then B, we look at the magnetized state. Now if we magnetize a material, how will the dipoles arrange themselves? So when the material is placed in a magnetic field during magnetization, most of the domains are aligned in one common direction. That is as shown here. So you see that in the process of magnetization, the dipoles are starting to align in a common direction. That is, these dipoles were facing this direction, but they are now facing towards a common direction. That is, they are facing towards that direction. So like in this case, we can conclude that the north pole is in this side because that is where the dipoles are originating from. Then the south pole is in the other end because that is where the dipoles are pointing towards. Just like the lines of force or magnetic field lines, they originate from the north pole towards the south pole. So in the magnetized state, the dipoles are starting to align. To align is just to arrange themselves in one line. They are starting to align or to point in a common direction. So when the material is placed in a magnetic field during magnetization, most of the domains or the dipoles are aligned in a common direction. So when this alignment has taken place, the material is said to be magnetized. That is, when all the domains arrange themselves, when the domains arrange themselves in a common direction or the dipoles, then the material is said to be magnetized. So in this state, actually the material is magnetized. Yes, it is magnetized, but it is not fully magnetized, meaning it is magnetized to some extent, but when you bring it to closer to a stronger magnetic field, its level of magnetization can also be increased. That is, it can be magnetized further. So if the magnetized field, if the magnetizing field is strong enough, all the domains get aligned. So if you place the same material in a very strong magnetizing field, all the domains get aligned in a common direction. So the material is then said to have to be magnetically saturated. So in this state, the material is said to have reached magnetic saturation. So magnetic saturation simply means it cannot be magnetized further. That is, it has been magnetized to its limit or to the maximum. So it cannot be magnetized further. And remember that anything that causes the dipoles to disalign actually causes demagnetization. So demagnetization is the opposite of magnetization. So we look at various methods of magnetizing and demagnetizing a material in our next class. So in summary, we have simply said that, so you can be brought a question, maybe they may ask you to sketch the arrangement of the dipoles within the domains under the following states of magnetism: A, unmagnetized state; B, magnetized state; 3, magnetic saturation. So in the unmagnetized state, you just draw the dipoles but facing in anyhow direction or in opposite direction. In magnetized state, you draw the dipoles starting to align in a common direction. Then in magnetic saturation, you draw the dipoles fully aligned in a common direction. That is, they are all facing in a specific direction and they are actually parallel to each other. So in summary, we are saying that the domain theory simply states that when a bar magnet is broken into pieces, The pieces retain their magnetism, each having a north pole and a south pole at its end. Then magnets consist of smaller magnetic groups called magnetic domains. Then the domains comprise of smaller subatomic magnets called the dipoles. So a magnet is made up of the dipoles, or the tiny magnets or subatomic magnets called dipoles, which are influenced to face in one common direction, hence causing different what? Polarities. So remember, the alignment of the dipoles is what causes different polarities. Like for this case, I can easily conclude that my north pole is here because this is where the dipoles are originating from. Then this is my south pole is on the other end. So during magnetization, the dipoles are influenced to face in one common direction. Then once all the dipoles are fully aligned, the material is said to have reached magnetic saturation and it cannot be magnetized any further. Then whatever causes the dipoles which are aligned in a certain order to disarrange or to disalign causes demagnetization. It causes demagnetization. So we've come to the end of our class today, but we need to discuss the quote of the day. So how did the quote of the day actually state? So the quote of the day stated that sorry, I don't have a solution for what you should do in order to live a happy life. Instead, I have a solution for what you should do in order to live a sad life which is full of regrets. And the solution is trying to please everyone. So what does this particular quote actually mean? So the quote simply means that you should design your life in such a way that it makes sense to you and it makes you happy. And it may not make, remember, when you've designed your life such that it makes you happy and you are okay with it, it may not make everyone around you happy. But as long as you are happy with it, then that is enough. Remember that sometimes it's okay not to be okay. Yeah, don't live your life trying to please everyone. Do what you feel in your heart. That is the right thing to do and what you are passionate about. Then the truth is, you can't please everyone in life. Even Jesus Christ himself never committed a single sin while he was on earth, but was still crucified by the same people he died for. So what makes you think you can please everyone in the world? Yeah, that is insanity. So never stop doing something great just because you fear what other people will say. And remember this, when 99% of the people around you doubt your idea, two things are just about to happen. One, either your idea is totally wrong, or two, you are just about to make history. So the choice is yours. But for my case, I choose to believe in I'm just about to make history. And I wish you also believe the same. And lastly, always ensure that your desire for success exceeds your fear for failure. This is Kind Tuition Academy. Kindly hit that subscription button on YouTube. Thank you.